Follow the hint to its end and a strange rule shows up. There's a smallest meaningful tick on the ruler. Not a brick wall you crash into, more like the point where the word distance stops carrying information. That scale has a name, Planck length. It's about 1.6 times 10 to the minus 35 meters. If you try to shave below it, the act of measuring scrambles what you're trying to define. Here's the easy-to-hold version. To see smaller things, you use shorter wavelength probes, higher frequency light, sharper beams, tighter focus. But shorter wavelengths carry higher momentum. Higher momentum means more energy concentrated in a smaller region. That energy curves space-time. Push far enough, and the very probe you chose to reveal detail produces enough curvature to hide it. You try to resolve a distance. A horizon steps between you and the answer. This isn't a trick of the lab. Meade worked it out in thought experiments. Later analyses sharpened the logic, combine quantum uncertainty with gravity, and there's a floor to spatial resolution. Not a literal pixel you could peel off, but a limit on how much position can be specified before the notion of position melts into quantum gravitational noise. It's why physicists talk about quantum foam, Wheeler's phrase for geometry that flickers at tiny scales, like a sea whipped by a storm you can't calm. So what does foam really mean? It means that at Planck distances and Planck times, geometry itself is uncertain. The line you think you're drawing between 2 points frays. Angles wobble. Over big distances, all those jitters average out and space feels smooth. Down in the basement, the floorboards creak. Try to time a photon's flight with an idealized clock, and Wigner's thought limits pop up unless you tie the clock down and let the environment help. Either way, every upgrade you make to precision echoes back as disturbance. Backaction isn't a bug, it's the price of asking. Now remember the earlier lesson. To encode more detail inside a region, you shove in modes with tinier wavelengths. At first, that just raises the energy bill. Keep going, and geometry itself starts acting like a defender. The Bekenstein Bound walks you to a surface. The Planck scale tells you where the game clock runs out. Below that, closer and further, lose operational meaning because any measurement protocol that would tell the difference would create a black hole. People ask, could we catch the foam in the act? Maybe as a faint hiss riding on light from far galaxies. There were ideas to look for wavelength-dependent blurring of distant images, or travel time jitter that would smear sharp pulses. If spacetime had a simple grain, high-energy photons might arrive a touch slower or images would fuzz more than optics allow. Astronomers have hunted for that, and the null results bite. Limits from sharp images and gamma-ray bursts say, if there's foam, it doesn't act like naive gravel. No easy dispersion. No obvious blur. Whatever the microstructure is, it respects Lorentz symmetry to exquisite precision at the energies we can probe within current sensitivities. Down on Earth, people tried to listen with interferometers, machines built to measure absurdly small changes in length. The idea was that if space at tiny scales performed a random walk, the arms of a detector might pick up a correlated noise pattern, a jitter not from thermal drift or seismic hum, but from geometry itself. Those experiments haven't heard a telltale signature. They've turned the dial into constraints instead, ruling out broad classes of simple, holographic noise models and pushing any would-be pixel size down near the Planck area or into more subtle encodings. Absence here is information. It says the code, if there is one, is cleaner than our first guesses. So why call it a pixel if it isn't a grain you can touch? Because the right metaphor isn't sand, it's bitrate. Think of the Planck scale as the maximum resolution unit for spacetime's description that doesn't break the channel. You can oversample an image all day. If the scene itself only contains so much detail, the extra pixels repeat the same information. At sub-Planck attempts, you're oversampling a scene whose fine print is protected by the interplay of uncertainty and gravity. The map can't get sharper without crashing the renderer. Here, S where the earlier surface hint and this minimum-length story lock together. If the content that can fit inside a region is ultimately priced by the area of its boundary, then the elementary accounting chip is a patch of that boundary about 1 Planck area in size. The pixel isn't a cube in the bulk. It's a tile on a surface that keeps the books. That's what the equations keep saying, from black hole thermodynamics to how entanglement entropy in quantum fields hugs the area of a cut. The deeper you push into the room, the more you're forced to read the walls. There's a practical sting to this. Every time you design a measurement to squeeze more detail, the Heisenberg toll booth goes up and gravity steps closer. In the lab, that shows up as back-action noise you struggle to cancel. On the edge of a collapsing star, it shows up as a forming horizon. Same rules, different stakes. The world feels smooth and continuous because, averaged out, it is. But underneath, there's a minimum resolution that keeps the show coherent. And if detail really lives on surfaces, then the ultimate surface might be running the whole game. Horizon ledger, where reality writes itself. Stand one hair outside a black hole and think like an accountant. There's no inside you can audit. There's only a boundary, an event horizon, that never shows you a line item directly, but somehow keeps perfect books. That's the weird shift Bekenstein and Hawking forced on us. Reality seems to write to surfaces. Here's the rule the horizon enforces. The number of microstates, the possible arrangements consistent with what you see, scales with the area of that horizon in Planck units. Double the area, double the capacity for distinct states, not because the interior volume doubled, but because the ledger, the surface, got more tiles to write on. The formula has a stark beauty. Entropy equals a quarter of the area measured in Planck areas. It's an area law, and black holes are its strictest auditors. Why a ledger? Because the horizon's job is to separate what you can influence from what you can't. From your side, any attempt to throw in a photon, a notebook, or a star resolves as one change. The horizon's area adjusts. You might never see the notebook again, but you watch the boundary swell by an amount that exactly covers the extra information now hidden from you. You lose access. The ledger gains a bit count. Feel it at the human scale. A single photon climbing toward that surface redshifts, its frequency sags, its identity blurs. The closer it gets, the longer it takes to cross in your clock, the more its energy spreads in your description. When it finally disappears beyond your causal reach, the horizon's area has already nudged upward. One more binary distinction, that photon was either here or gone, has been priced and recorded. You didn't track the interior, you watched the wall update. This is where Hawking radiation sneaks in as a second column in the ledger. Quantum fields near the horizon don't stay empty. Pairs of excitations can become real, with one partner effectively trapped and the other escaping as thermal radiation. That radiation carries entropy away, which means the horizon's area shrinks in step. Deposit information by throwing stuff in. Withdraw by waiting for radiation correlations to leak it back out. The bookkeeping balances, but not in a way that feels intuitive at first, because the digits aren't letters on pages. They're geometric quanta of area. Now scale the stakes. Black holes are the tightest vaults nature builds. Pack too much detail into a region and gravity mints a horizon that guarantees two things. You won't see the insides, and the boundary will remember how much you can't see. It never forgets the total count. The hard question is how the ledger encodes structure. The consensus today leans away from naive erasure. The state of the radiation and the state of the horizon are entangled in subtle ways that can, in principle, reflect what fell in. The page is complete, but the handwriting is encrypted by the dynamics of quantum gravity. Meanwhile, something else was happening in quantum field theory far from black holes. When you split space into two regions and ask how entangled their fields are, the entanglement entropy you compute also scales with the area of the cut between them. No horizon, no singularity, same area law. It's a whisper that the ledger logic isn't a black hole-only rule, it's a habit of the vacuum. The universe seems to count connections across boundaries, not inventory inside rooms. But there's a complication the horizon forces the moment you try to overfill it. Store more and the horizon doesn't bend to your wishes. It grows. The radius increases so the area law keeps pace with your ambition. That's geometry doing enforcement. You demanded more states behind the veil. The veil expanded so the bound still holds. It's the same theme we hit in the lab, just turned up. You try to cram detail, reality pays in shape. If surfaces keep the books, then our bulk stories, distance, volume, the feeling of a 3D world, might be playback. That's the unsettling turn the holographic principle makes precise in certain settings. The surface isn't just a receipt, it's the code that can, in principle, reconstruct what the interior does. In the best understood examples, the screen is a boundary where a quantum theory with no gravity lives with negative cosmological constant, as in anti-de Sitter space. And the movie is a gravitational world in one extra dimension. Compute on the edge. Watch a universe evolve inside. People ask for a mental anchor. Try this. You're in a room, and nothing you do to the furniture adds new fundamental digits to the world's description. You can rearrange, you can heat it up, you can write novels. The deep limit to how many distinguishable states that room can support is stamped on the walls. The horizon is the extreme wall. It sets the ultimate rate card for information you can hide from the outside. That flips our storytelling instinct. We want the center to matter most. Nature points us to the border. The ledger writes on area. The tally lives on the edge. And if our 3D lives are priced by 2D boundaries, we have to ask the next question carefully. If the ledger holds the code, are we living in the projection? Two-dimensional universe, three-dimensional lives. If surfaces keep the books, the bolder claim is this. The book can rebuild the story. That's the holographic principle in plain terms. The full physics of a volume can be encoded on a boundary one dimension lower, like a hard drive that stores the movie of a world you then play as 3D experience. In certain universes, we don't just suspect this, we can do the math. On the boundary lives a quantum theory without gravity. Inside emerges a world with gravity and curvature. Compute on the edge, watch geometry answer. Here's the intuition flip. You're in your room. You breathe, pace, talk, think. It feels like the richness lives in the air between the walls. Holography says the fundamental digits, how many truly distinct states that room can host, don't live in the air. They're priced by the surface. The walls hold the code, the volume is playback. Rearrange the furniture and you remix, but you don't mint more underlying capacity than the area allows. So what pushes this beyond metaphor? Start with black holes. Entropy is a quarter of the horizon area in Planck units. That's already a flashing sign that nature counts boundary tiles. Then look at quantum fields here and now. Carve space into two parts and ask how entangled they are. The answer to leading order scales with the area of the cut, not the volume on either side. It's an area law again, far from any singularity. Two big clues. And then the clincher in a special classroom of universes. A duality where a lower dimensional, non-gravitational quantum theory equals a higher dimensional gravitational one. Not resembles, equals. That's a working example of the holographic principle. Human stakes show up fast. If the world's deep description is boundary code, identity, locality, and cause and effect look different under the hood. Yourself isn't a unique bead somewhere in the bulk. It's a robust pattern that the code can support, spread across many boundary degrees of freedom. Locality, the rule that only nearby things interact, may be an efficient summary of how the code organizes correlations, not a bedrock rule. Two regions that feel far in the room can be tightly bound neighbors in the code if entanglement knits them closely. And causality, the arrow of influences, has to match how information can flow on the boundary. The familiar light cones in the bulk are a translation of boundary bandwidth and constraints. Try a microstory. A sealed box sits on a lab bench. You keep pumping in structured light, spin states, phonons. Inside, it never feels fuller in the holographic sense. The lid, your boundary, just has to get denser with code. Each extra distinguishable microstate you try to create inside is paid for by more complex correlations on the surface. You're not filling air. you're saturating a ledger. Here, S where the mind protests. If we're encoded on a boundary, where's the screen for our actual cosmos? In the examples we understand best, the boundary is literally at infinity, a distant surface with clean mathematical properties. Our universe seems to expand with a small positive cosmological constant, not the negative one that makes the math tidy. The screen for our world isn't settled. Some proposals aim at a cosmic boundary tied to the far future, others at horizons associated with observers. The honest state of play. The idea is strong. The exact screen here is under construction. Meanwhile, evidence runs through behavior, not billboards. Black hole area laws don't blink. Entanglement scaling keeps pointing to boundaries. The Ryu-Takayanagi relation in those well-understood AD-SCFT dualities says the entanglement between two regions in the boundary theory equals the area of a minimal surface in the bulk that spans them. That's geometry literally reading out of correlations. Strengthen entanglement on the boundary, and the bulk path between regions shortens. Loosen it, and the path stretches. Distance becomes a function of connection. That flips how you file space. Don't start with a grid and place matter in it. Start with a network of quantum degrees of freedom and their entanglement. Ask what emergent notion best summarizes who talks efficiently to whom. The answer is geometry. The room is the output of the code, not the other way around. Break links in space phrase, knit links in space holds. This changes how we think about error too. If the bulk is playback, smoothness is stability of code words. That's why naive grain searches have come up empty. A good code hides micro errors from macro observers. What you call a table is a high-fidelity pattern resisting noise. You experience solidity because the encoding is redundant and the checks run constantly. None of this makes life less real. It gives it a different kind of real. You're not a smear on a wall. You're a pattern with persistence, protected by constraints that keep chaos at bay. Meaning grows in how efficiently the code carries you forward. And if the world prices detail by area, our next job is to listen for the projector's hum without mistaking the movie for the machine. The screen may be far, but the rules it sets are right here, searching for every scene you live. Experiments chasing space-time noise. If the code runs on a surface, maybe it leaves a hum. Not a tone you can hear, more like a universal background hiss, geometry's own noise floor. That's where the hunters come in. Experimentalists who build machines that can feel a proton's width change across kilometers and ask if spacetime itself twitches. Start with the idea of holographic noise. If there's a minimum resolution, distances might fluctuate ever so slightly, not as a classical shake, but as an irreducible jitter tied to the information limit. The dream signature wouldn't be random junk. It would be correlated, the kind of pattern two separated detectors would share if they were both reading the same underlying code. Interferometers are the natural stethoscopes. You split a laser beam, send each half down long perpendicular arms, bounce them off mirrors and recombine them. If one arm stretches by a whisper compared to the other, you see fringes shift. Do this with high power, superb mirrors and isolation from the world's rumble, and your device can register distortions smaller than a proton's diameter. That's already how we caught gravitational waves from colliding black holes. The question here is subtler. Is there a residual variance no engineering can scrub, because spacetime itself has a finite bitrate? A few years back, a team tuned two adjacent interferometers, side by side, to hunt for shared noise, correlations that couldn't be blamed on local hardware gremlins. The pitch was simple. If the pixels of space smear positions in a universal way, two independent instruments looking at nearly the same patch of geometry might hear the same murmur. If the murmur was there, it would show up as excess cross-correlation at specific frequencies, beyond what thermal jitter, seismic drift, or electronics could explain. Now here, where reality pushes back. The instruments got cleaner and cleaner, and tentative excesses reported in early analyses did not survive improved background modeling and upgrades. The correlated excess didn't stand up once backgrounds were properly modeled and new knobs were tightened. You can write that as a disappointment. The better way to say it is, those nulls became measurements. They drew a box around entire classes of simple, grainy space models that would have left a telltale blur or dispersion. If geometry has a hum, it isn't a coarse rattle. Meanwhile, astronomers turned the sky into an interferometer of a different kind. If quantum foam slowed higher energy photons even a hair, then light from gamma ray bursts, catastrophes billions of light years away, should arrive with energy-dependent delays. You'd see the high-energy photons lag the lower ones as if space were a slightly sticky medium. Observatories stacked events, checked arrival times, and squeezed the uncertainty. The delays didn't show. Within tight bounds, photons of wildly different energies ran neck and neck across cosmic baselines. Simple, speed-of-light through foam stories got pushed off the table, placing strong constraints on Lorentz-violating dispersion. There's another angle, images of distant quasars and active galaxies. If spacetime were a granular lens, scattering would smear points into fuzz beyond what optics and interstellar dust predict. Telescopes pulled crisp fringes from the far universe. The crispness itself set a lower limit on any putative jitter. Space, if it foams, does so with a discipline that keeps Lorentz symmetry intact at scales we can probe. No sloppy hiss. No obvious pixelation in the raw picture, only upper limits on any such effects. Back on Earth, quantum opticians tried squeezing light, reducing uncertainty in one quadrature to beat down shot noise, hoping to pry open a window where any irreducible geometric noise would stand alone. Each upgrade made instruments more sensitive to real physics and less forgiving of fantasy. The more you clean, the more the remaining hiss must be either ordinary or deeply conspiratorial. So far, the remaining hiss is ordinary. Thermal tails, thermal lensing, coding losses, seismic upconversion, quantum radiation pressure noise. The list is long, the fixes are clever, the universe stays quiet. This is where theory re-enters, less as a rescue than as a reframing. If the deep description is an error-correcting code, then naive grain won't leak into macroscopic observables. Good codes hide micro-errors. They don't produce white hiss, they produce stability. Entanglement can stitch fluctuations into patterns that look smooth to any local probe. What would a real signature look like then? Not random jitter, but correlation structured by causality. Specific non-local patterns tied to causal diamonds, or entanglement witnesses encoded in subtle phase relationships between distant detectors. People are working on that. Some proposals sketch cross-correlations between widely separated interferometers that share portions of their causal past. Others aim at tabletop detectors tuned to relational observables, measures that compare two clocks or two rulers in ways that cancel environmental drift, but could expose a shared, geometry-level constraint. There's even work using atom interferometry, where you split matter waves and let them sample spacetime along different paths before recombining, in hopes that any fundamental discreteness would fog the phase predictably.